This is the Lesson 20 College Algebra Preview Exercises. The general form, or the quadratic or polynomial form of a quadratic function is any function that has the form ax squared plus bx plus c. So f of x equals ax squared plus bx plus c. A, b, and c are real numbers, and a is not 0. Otherwise, this term would be gone, and you would just have a line, bx plus c. So this is different from a linear function because it has an x squared term, and the graph of a quadratic function is called a parabola. It's this U-shaped looking graph that either opens up or down. So the parent of all quadratic functions is f of x equals x squared, and every other quadratic function is a transformation of f of x equals x squared. The point 0, 0 on x squared, that's called the vertex of the parabola, the relative min on y equals x squared, that's called the vertex. The graph of x squared and the graph of g of x, which is a transformation of x squared, given by 2 times x minus 1 squared minus 3, are both graphed below. So we want to write a brief description of the transformations applied to the parent function f to obtain the function g. So looking at this formula, we've got a times 2 outside. That's going to give us a vertical stretch, which takes all our y values and multiplies by 2. Then we always do any stretches and shrinks first, so we did that first. And then we have these shifts, a right 1 and a down 3. This is inside, so it's kind of the opposite of what you think. So this is going to go right 1. This is outside, is exactly what you think. It's going to go down 3. So then we shift right 1 and down 3. And you can see that result in the blue graph here. It definitely looks like I had a vertical stretch. It's taller than the green graph. And we took the vertex 0, 0, and we moved right 1 and down 3 to get the vertex of the new graph. So we're going to show how to change each coordinate of the following points according to the transformations that have occurred to f. So the first 2 points are done as an example. So negative 1, 1. First, we do the vertical stretch, which means multiply y by 2, so that becomes negative 1, 2. We took the y coordinate, multiplied by 2. Then, to shift to the right, we add 1 to the x, so we take our negative 1, we add 1, we get 0, 2, and then we subtract 3 from the y to go down 3, so that ends up at 0, negative 1. You can read through the 0, 0, 1, and then the 1, 1. First, we multiply y by 2, so we have 1, 2. Then we add 1 to the x, so we have 2, 2. And then we subtract 3 from the y, so we have 2, negative 1. So 2, negative 1, that's the point we just found there. So what are the coordinates of the vertex of g? The vertex is right here. It's at 1, negative 3. And could we have identified the coordinates of the vertex just by looking at this formula? Yeah, because the vertex of x squared are 0, 0, and we know that this is going to move right 1 and down 3, so the new vertex would land at 1, negative 3. So note that the y-axis is a line of symmetry for the original graph, y equals x squared, right? If I folded over the y-axis, it would lie right on top of itself. But my transformed graph also has a line of symmetry, and it's the line x equals 1. So this vertical line right here acts as a mirror for the transformed function. If you fold it over that line, it lies on top of itself.